Welcome back to ECE 442-542. Hopefully everyone can hear me here and see the screen. I know it's going to be hard looking around every head that's in the room, but we'll figure out if we can actually find everyone. You have something due tomorrow, homework number 7. And that should be on controller design. Your project is due on Wednesday, and homework number 8 is due on Thursday. And that's an extra credit assignment, but you also will need that information on the final exam. So don't assume that that's not going to be included on the final. The final will be uniformly distributed across the material that we've covered all semester. It won't be emphasizing the most recent material in the class. You'll be responsible for all of the material, but you can tell just by paying attention in class that the material does build on itself. So if you know the latter part of the class material, you probably understand the beginning pieces, but you do need to have all of that in place for the final exam. I'm thinking I will have a final exam review session. Is that reasonable? I guess I'm really sampling a small number of students, but I do believe I've been given a room. It's not going to be in this room, but it will be in Harville 204. The final exam review session will be from 4:30 to 5:45 on reading day, which is the 2nd of May. That will be the day after our last class and the day that homework number 8 is actually due. Teacher course evaluations are actually due a day before that on Wednesday, and those close at 11:59 p.m. Don't put that off to that close to the time. Hopefully you'll do that before then. And our final exam is in this room on a week from Thursday. It's the last day of finals from 1 p.m. to 3 p.m. I am making available some additional office hours beyond the last day of class, and they're listed here. And it's every day prior to your final exam, except for Saturday and Sunday. I will give you those 2 days off, and these are the days, and if you can't make those times, let me know, and we'll see if I can answer those offline or some other way. What I want to do today is review what we did last time. We're in Unit 8, which is State Space Controller Design. We want to work through a full state feedback problem, which if you are applying a full state feedback design strategy, you're not yet including a reference input, and for that reason this is referred to as a regulator design. This will now regulate everything to 0 or to a steady state condition, which is 0 after starting at some initial condition location. And that K, that full state feedback gain matrix, tells the system how to behave, and we may want to do more than that. We may want the system to do more than just behave. We may want to tell the system where to go. And telling it how to behave requires, if we want to tell it how to behave arbitrarily, then we need to have that system being controllable. We'll talk about controllability, and that allows us then to locate our closed loop poles by that full state feedback gain matrix anywhere we want in the Z-plane. Then we'll introduce a reference input, and that now allows us to command the system to move to a particular location or track a certain reference input that we may want to introduce. And then if we have time, we'll talk about a mass spring damper system. here's our review. We have our system represented as a state space representation. We have the system matrix phi, we have the input matrix gamma, and we have the output matrix H, and I'm not assuming a direct feed-through matrix in the output expression, which could be a plus J U of L. And that just makes it a little bit easier when we start looking at transfer functions, but you could derive the same or walk through the same derivation to obtain a slightly modified transfer function if you were interested in having a non-zero direct feed-through term in the output matrix equation for y. We want to now look at feeding back every one of those state variables, x, scaled in some way, k. And that's our matrix feedback gain matrix, and depending on how many inputs we have, if we have m of those Michigan inputs, and if we have N or Nevada state variable components, our feedback gain matrix is going to be dimensionally m by n to be compatible with gamma and phi, so that we can now combine the product of gamma k with phi. In a block diagram form, we really now just have this description. If you simply erased that bottom feedback path, you would have your open loop system, which now has the input matrix gamma, the system matrix phi, and the output matrix H. With full state feedback, we're adjusting essentially how the system is interconnected, or we're influencing the dynamic behavior of that system. And in highlight, I've tried to explicitly show that there's no reference input commanding or telling this system where to go. It's just behaving the way that we want by the choice of the full state feedback gain matrix K. You can either write it in this way analytically, or you can think of it in a block diagram form. They are equivalent representations, and they both, I think, are helpful to understand how to utilize systems in a state space representation using full state feedback. The original dynamics of the system are determined by the eigenvalues of the system matrix phi. In this case, let's look at an example. Let's say phi is equal to this two-dimensional or 2 by 2 matrix, 2, 1 in the first row and 0, 0 in the second row. What are the eigenvalues? If you've had a linear algebra class, can you tell me what the eigenvalues are? For some reason, I felt like we were too bright, but maybe we weren't. I was having trouble seeing the screen. Now are you going to fall asleep on me if I have dimmed the lights? I know if you're following along at home, that probably really impacted you, but it might impact the students listening here. You're in for it if you're at home, and I now have dimmed the lights. But you can brighten yours independently. Show of hands, do you want me to turn the lights back up? All right. So it only takes one, right? Our eigenvalues here are what? This is a upper triangular matrix, which means that the eigenvalues are on the diagonal. Our eigenvalues in this case, we don't have to go through what I show on the screen, which is this determinant of zi minus phi. You can, by inspection, if you understand this process, you can tell that the eigenvalues are at 2 and 0. Our open loop poles, or the dynamic behavior of this system, are influenced by modes at 0 and 2. The 0 one is quick, but the one at 2 is problematic. That's unstable. And the reason, or the justification for why the eigenvalues are the poles of our system, you can see if you compare this determinant expression for zi minus phi with the transfer function description, and in the transfer function you're taking the determinant of zi minus phi, and that's in the denominator polynomial. That's the poles. In this case, we have z times z minus 2, and that then you can, I hope, see what values of z cause that expression to vanish or become equal to 0, z equal to 0, or z equal to 2. You didn't have to know anything about upper triangular or diagonal matrices. You could brute force put through the calculation on the determinant of zi minus phi and solve that quadratic in this 2 by 2 case and find out where your eigenvalues are. We obviously may not be happy with the behavior of the system, and for that reason we will introduce full state feedback, or say that we can now scale each one of these state variable components. It has two components, x sub 1 of k and x sub 2 of k. K, the full state feedback matrix, is actually a row vector, and it's one row tall and 2 columns wide. K is a 1 by 2 matrix, and that now allows us to combine it in with gamma to give us the change that we want, or trying to tell the system how to behave. And if we're trying to pick K or design K, you already know a fair amount on where you might want those closed loop poles to be located. We've already talked quite a bit about performance specifications, or circles, hearts, and wedges, or settling time, percent overshoot, and peak time. Those performance specifications could give rise to dominant poles, the poles that dominate your system behavior. Those are the triangles that are closest to the unit circle. And then if you had 6 closed loop poles, you could say, oh, I'm going to make the dominant ones these 2 to satisfy my circles, hearts, and wedges, and the other 4 I'm going to just put at the origin. So they are fast relative to the dominant ones, and now you have those dominant poles influencing the performance of your system based on settling time, percent overshoot, and peak time. And you'll need to know all of this for the final exam. So can you, given these performance constraints or conditions on settling time, percent overshoot, and peak time, determine where you want your poles to be, a dominant set of poles? Once you've determined these dominant poles, you can now create this characteristic, or this desired polynomial, delta sub d, and we're going to set that equal to the determinant of zi minus phi sub c, which contains all of the unknown parameters in our full state feedback gain matrix K. But first, in order to do that, let's remind ourselves where that desired polynomial comes from. We have desired closed loop poles, let's say at 0.8 plus and minus j 0.2, and that now we can say gives rise to 2 linear factors with complex poles. Those poles are conjugates of each other, And if you now multiply those two factors together, and here you might want to pay attention to the black and the blue is now one of the terms in each factor, and the black is the other, and you're now, the cross products cancel because these are conjugate pole pairs, or this is a conjugate set of pole pairs. We now have z minus 0.8 quantity squared minus the quantity j.2 squared. The j squared gives us a -1, and in fact, if somebody now told you, I want closed loop poles at 0.8 plus and minus j.2, you could immediately start at that bottom line. You don't need to rederive this set of relationships to convince me that you know where those poles are located. I'm just doing that so that you understand that if I now say, oh, we wanted our polynomial to have these as its roots, here's how I'm going to build that polynomial. Z minus the real part, quantity squared, plus the imaginary component squared. That's where I would start. So you can start here once you're given desired closed loop poles. And now simply multiplying that out, you find the desired polynomial, delta sub d of z, is at z squared minus 1.6z plus 0.68. That's where we want our polynomial to be, or what we want it to equal, by the appropriate choice of the full state feedback gain matrix. In this case, it has two parameters in it, k sub 1 and k sub 2. We're now finding delta sub k, which is the polynomial that contains these yet to be determined coefficients k1 and k2 that parameterize our full state feedback gain matrix. We now have zi minus capital phi sub c. Capital phi sub c is the closed loop system matrix that is related to the open loop system matrix via phi minus gamma k. Plugging all of those values in for our specific example and combining gamma with k, we now end up with a 2x2 matrix that contains, sprinkled throughout, k1 and k2. Here k1 and k2 only come in the second row because our input matrix had an all zero top row. So there's no way those k's are going to be influencing the top row terms in our phi sub c or zi minus phi sub c expression. Just as a way of a check on your algebra or your mechanics. And the determinant is simply the product of the diagonal terms minus the product of the off-diagonal terms. That now allows us to generate a second-order polynomial that we'll now be able to use or compare with the desired polynomial. We want this delta sub k of z, which contains k1 and k2 in the linear coefficient and the constant coefficient. We want to pick k1 and k2 to give us delta sub d of z. And delta sub d of z then has those two coefficients already determined. We now generically have two equations comparing or equating like coefficients between those two polynomials. We have two equations and two unknowns. The two unknowns are k sub 1 and k sub 2. The two equations come from the z sub 1 coefficient, which says now we want minus 1.6 to equal minus 2 plus 3k sub 2. And generically, that equation could contain k sub 2 and k sub 1. In this particular example, it only contains k sub 2, and for that reason we can immediately solve for k sub 2. The constant coefficient, or the coefficient that scales z to the 0th power, is now 0.68, and that needs to equal 3k sub 1 minus 6k sub 2 by the choice of k sub 1 and k sub 2. We've already determined k sub 2, and we'll reuse that to eliminate the unknown k sub 2 in this equation, where k sub 2 is now 0.4 over 3, and 3 goes into 6 2 times. That allows us to clean up that right-hand side, and we now have 0.68 equaling 3k1 minus 2 times 0.4, or 0.8. We combine those known constants on one side, 0.68 plus 0.8, to get 1.48, and that equals 3k1, but 1.48 is about 1.5. So if I have $1.50 and I split that 3 ways, I have 50 cents. So my K1 better be about 50 cents, or it's 0.4933. That seems reasonable for a value for K sub 1. We now have K sub 1 and K sub 2 determined. That's all we need for full state feedback. And this tells the system how to behave. How is that system going to behave? Well, it better behave in such a way that it has modes at 0.8 plus and minus j.2. As a sanity check, let's just verify that. Let's now apply full state feedback. Again, all of this is a review, but I'm just hopeful that you're following along and you can reproduce something like this on the final exam. If you're given a question involving even difference equations, and now you are asked to put it into a state space representation, you should be able to do that. Then once it's in a state space representation, can you select a full state feedback gain matrix to produce the closed loop system matrix that you want? In this case, we start with the open loop system of phi x plus gamma u on the right, both of those x and u at the present time instant. Those equal, and now you can see, I hope, that you need to correct my notes. How many more errors have I slid through or slept through? But that's now x at time L plus 1 is equal to phi x of L plus gamma u of L, or plugging in u of L is equal to minus k x of L. We can combine or factor out the common state vector x of L to give us the parameterized form of our closed loop system matrix, where it's parameterized in terms of the open loop system matrix phi, the input matrix gamma, and the full state feedback matrix k. And from this expression, if you do nothing else on the final, and if I give you a phi that's 3 by 3 and a gamma that's 3 by 2, can you tell me what k needs to be dimensionally? Maybe not what each of the variables are, but how big is k? Or what are the dimensions of k? What did I just say? You'll have to remind me. Phi was 3 by 3. Gamma has to have the same number of rows as phi, so you know gamma has to be 3 rows tall, but here I just said let's let Michigan be 2. M is 2, so gamma is 2 columns wide. How big is k? Pardon? It needs to be 2 by 3. It has to be dimensionally compatible with this formula, meaning it has to have 2 rows to account for the 2 columns in gamma, and then it has to have 3 columns to account for the 3 columns in phi. And now this gamma k product, which is 3 by 2 times a 2 by 3, gives us a 3 by 3 matrix. And we would have 6 unknowns in that k matrix. Easy problem for the final. Right? That means you have maybe more flexibility in K. So now if you're talking about multi-input, multi-output systems on your project, now you have more than poles that you can maybe deal with. You could place all the poles. If gamma was controllable through its first column, you could place the poles wherever you want with just the top row of K. Now you have a second row, or you now have some flexibility. Now maybe you can shape the eigenvectors of this phi minus gamma k. So there's different questions that now become answerable or askable when we're in a multi-input, multi-output setting. Just saying. So these are the kinds of questions you might have to confront beyond this class. Oh, wait a minute. We never did a K that was multi-dimensional, or we didn't deal with full state feedback when we had more than one input. Well, now maybe you get a feel for, oh, that maybe gives us some flexibility that we didn't talk about in 442, 542. And how can I use that flexibility? Hopefully to your benefit, maybe to reduce the size of the input that comes in to move your system or make it behave the way you want it to behave. Maybe you use it to shape the closed loop eigenvectors, which tells your system how it's actually moving, not only in time but also in direction with x sub 1 and x sub 2. I know you're just dying to start experimenting with all of this. But here I removed some of that motivation by making gamma only associated with one input. Now gamma is a 2 by 1, and I've actually collapsed my gamma. We returned to our original example. We have phi is now 2 by 2, and we have our gamma, which is 2 by 1, and now I'm simply substituting in the known values for k that are supposed to give us our closed loop eigenvalues where we want. And where we wanted those closed loop eigenvalues better fall out of the next check. The next check is to compute the determinant of zi minus phi sub c. Just to see if what we claimed that k was going to do, if it actually does make the system behave the way we want it to behave. Combining those two matrices gives us now a 2 by 2 matrix involving unknown parameter z, but those are the values that we want in our closed loop polynomial. And in this case, wow, it does give us what we want. That shouldn't be a wow, that should be of course. Unless we've done our algebra wrong or made some calculation errors, this should be a check on our math or on the process. And in MATLAB you could just say EIG of phi sub c, and it should now give you closed loop poles at 0.8 plus and minus j 0.2. Or if you now factored that z squared minus 1.6 z plus 0.68 into a z minus a quantity squared plus something else squared, oh, that's the structure that he was talking about earlier and I don't have to do anything more. I now know exactly where those poles are. Or if you don't see that, you can simply apply the quadratic formula and now determine that the two roots to that second order polynomial are complex conjugates of each other, and those are the desired closed loop poles that we were after. I'm kind of just reading to you, aren't I? But you're following along. Thank you. Thank you for your support. I feel like a commercial. We have to do a commercial break, right? We've been in it for a while. But now let's talk about controllability, or answering this question. When is it possible to find a gain K, or a full state feedback gain matrix K, to make our system behave however we want? Now I want my system to have poles at 0.7 plus and minus j.1. Is that possible? Well, if our system is completely controllable, we can locate those closed loop poles wherever we want by the appropriate choice of our full state feedback gain matrix K. That's the answer to this question. When is it possible for the full state feedback to position the closed loop eigenvalues or poles arbitrarily? Or when can the closed loop behavior of the system be anything that we want? The answer, and I'm not going to just allow you to state this on the final, you'll need to compute this. But the answer is when the system is controllable. And now I'll give you the definition of when a system is controllable. A system is controllable if and only if this matrix, script C, which I'm going to refer to as the controllability matrix, when that matrix is full rank. And we can build that controllability matrix by just knowing the system matrix phi, this is the open loop system matrix phi, and the open loop input matrix gamma. And we just build this up. We just stack these products. Each of these products forms a column or a set of columns that's gamma wide. It's M wide. Everything is N tall. And we now put gamma in the first partitioning location in this script C matrix. Then we form the product of phi with gamma. That now forms a new set of columns, and we stack that to the right of gamma. Then I wouldn't compute phi squared. I would just hit phi gamma on the left with phi. And now you have phi squared gamma. Stack that next to the first two sets of columns, and you just keep going with this phi scaling phi gamma product, or phi to the n whatever product times gamma, up to n minus 1. Again, n is the dimension of the system, which is the number of rows or columns in the system matrix phi. If you have a 10th order system, phi is square, it's 10 by 10, and we now, to build this controllability matrix, we would need to have gamma phi squared gamma, up to phi to the 9th times gamma. Then we want that collection of columns and now rows to have full rank. What does that mean? For a matrix to be full rank. Is that a new term? It may be. Full rank now means that, well, here, what's the dimension of C, script C? It's Nevada tall by Nevada times Michigan wide. So if we have more than one input, it could be wider than it is tall, this controllability matrix. If little m, if Michigan is 2, if we have 2 inputs, now this controllability matrix is Nevada tall, but it's 2 Nevada wide. So it's not necessarily square. But for this system to be, or for this matrix to be full rank, we need all of the rows to be linearly independent. That means we would, did I put a dimension on Nevada? I didn't, did I? Not in the last few minutes. But if I said Nevada was 10, numerically a value of 10, then we would have 10 rows and 20 columns. We need 10 of those rows, all of those rows, to be linearly independent. We would only need 10 of the 20 columns to be linearly independent to be full rank. But we need this matrix, potentially non-square, to be full rank. That means we want all, in this particular construction, we need all of the rows to be linearly independent. Now if we have one input, now this controllability matrix is square and full rank. Well, if we have n rows and they're linearly independent, and then we also have n columns and they are linearly independent, we need the determinant of that matrix to be non-zero. It could be negative, it could be positive, you don't want it to have an end result. If we take the determinant of this square matrix that the controllability matrix now becomes, if we have a single input system, as long as the determinant of that matrix is non-zero, our system is controllable. Let's go through an example. Now we have a big state of Michigan and a big state of Nevada. Michigan is 1, Nevada is 2. We have one input. What's our controllability matrix? Oh, gonna have to wake up. Now you're going to have to guide me through this process. What does script C look like? I take the input matrix gamma and I squeeze that in right after the bracket. Then I just start doing the multiplications. And stop me when you feel like I need to stop. I should have stopped a long time ago, huh? I was going too fast. How many of these phi gamma products do I need? I just go up to little n minus 1 of those, raising phi to that power. In this case, little n is 2. I take 2 minus 1, that's 1. This is as big as my controllability matrix needs to be. Is gamma. That's one set of columns. And how many columns are in gamma? 1. So that's only one column wide. I now have 0, 3. And now I scale phi with gamma. Or that really just says scale the second column in phi by 3. Is another way of seeing this phi gamma matrix product with this structure for gamma. It's going to take 0 and scale the first column, and it's going to take 3 and scale the second column. The second column in phi is 1, 0. We scale that by 3, and we end up with 3, 0. That's our controllability matrix. Since it's square, since we had one input, little m was 1, we can check to see, and hopefully you can see that those rows are linearly independent or the columns are linearly independent visually, and say, oh, this system is controllable because we have this controllability matrix C is full rank. It has 2 linearly independent rows. They're not a linear combination of each other. Determinant of C better give us a consistent answer. This is now the product of the diagonals, diagonal terms, minus the product of the off-diagonal terms. In this case, I have 0 minus 9. Oh, minus 9. What's that tell me? My determinant's minus 9. What does that mean? I don't know, it's minus 9. That means it's not equal to 0. That's all you're after. That actually tells you that you have linearly independent rows or columns in this square matrix that you've now found its determinant for. There was no 0 eigenvalue in that set of columns or rows making up that matrix, and in this case then the system is controllable. So we actually sort of did this after the fact, but in reality you would make this determination and then say, okay, how do you want this system to behave? I can make it behave however you want since I know it's controllable. I can now find K1 and K2 for any arbitrary choice that you want for closed loop poles. Now, depending on how awake or asleep you are, I want to ask you the following question. Are we getting away with something? If you go back to what we have been doing up until Unit 8, did we have arbitrary freedom over where we could locate our triangles inside the unit circle? When we were designing proportional controllers, when we were designing PI controllers, when we were designing PID controllers, when we were designing stabilizing controllers, could we locate the closed loop poles arbitrarily wherever we wanted in the complex Z-plane? How come we can now? The answer to that first question is, where were the closed loop poles? In units 6 and 7, or units less than unit 8. Where were our closed loop poles in the complex Z-plane? If we stabilized the system, they would be inside the unit circle, wouldn't they? And where inside the unit circle were they arbitrarily located inside the unit circle? Now, let's just say we had, well, you're going, I don't know, I don't remember. Well, pull out a napkin. And now if you pull out a napkin and you go, well, I don't really remember what he's even talking about. What if I had a second order system and I had poles like that? And I tried to stabilize this system. I want my poles in the unit circle to be stable, and now where they are depends on how I've labeled my axis or where these poles physically are. Let's just say that maybe 1 is right here. Is this system open loop stable with, let's say, output feedback? No. Can it be stabilized with constant output feedback? Yes, if my drawing is somewhat, whoops, that was supposed to be red. My root locus would look like that, wouldn't it? Where are your closed loop poles? Are they anywhere inside the unit circle? They're only on the root locus, only on those red lines. And in fact, this system could be stabilized because the breakaway point occurs to the left of 1. And now you can't crank up k arbitrarily because you'll zip outside the unit circle. So there's a range of k for stability, but you can stabilize it. But we definitely don't have any point we want arbitrarily inside the unit circle. Now I come back to my question. You just said if my system is completely controllable, or my system is controllable, I can put my closed loop poles wherever I want. What? Are we getting away with something? What's happening? If I now had a second order system that had poles at whatever these are, 0.25 and 1.25, what is going on? What's the difference between this little picture over here? I'm not sure how I want to label that. What was going on there versus what we just talked about for the beginning of class up until now? Is there a difference? And the key word here, somebody's had breakfast, lunch, and dinner. They're full. This is the full state feedback. Over here in this yellow highlight, what do we have? This was output feedback. That may only be one parameter k. If we're in a second order system, we may only have one output that we can measure and scale and feed back. We have output feedback, and that limits how we can position these closed loop poles in the complex Z-plane. We've been talking today in Unit 8 about full state feedback, and full state feedback requires access, or that we have the ability to measure, scale, and inject into the system. We have access to each component of the state vector. So now that's basically saying, oh, you could only measure a combination of state variables when you had one output. Now we're assuming in full state feedback we can measure each of those state variable components independently. That's why we can now, if our system is controllable, we can do this arbitrary positioning of closed loop poles. We're assuming we have more capability when we say we have full state feedback. Are there any concerns? Well, yeah, we may not even be able to access all the state variables. If we're controlling a vehicle's engine, maybe we can't go into each cylinder and measure the temperature or the pressure or some of these other possibilities for determining the dynamics of this system. We may only be able to measure some combination or some indirect waveform associated with the dynamics of the actual system. But if we throw out that practical necessity, are there any concerns with having the full state feedback vector available? What are we still not really doing? Or, kind of a vague question, but if I go back far enough to this picture, if we're using full state feedback, we can tell the system how to behave, but can we tell it where to go? No. We have no reference input with just full state feedback. We can only influence the dynamic behavior. We can't really say, oh, I want you to go to 4, and it dutifully goes to 4. No, we can't do that. We can just sort of watch the system behave the way we want it to behave, which is maybe to have modes at 0.8 plus and minus j.2. Question?
Is the output not just a combination of different states?
So now is the output measurement, this y of L, that in this linear system representation is simply a linear combination of the states, isn't it? Because H is a constant matrix, and if we had one output, H is a row vector, and it linearly combines each of the components, x1, x2, all the way down to x sub 10, if our state vector was 10 elements tall. So now H is just linearly combining, and in some cases H might be 1, 0, 0, 0, everything else 0. Then our output measurement is the first state variable component. Or maybe Y is the sum of state variables 2 and 6. It depends on what H is. It really depends on our system and how we've represented it in this state space representation. Yes, our output is simply a linear combination, and so now, instead of independently measuring the state variables, with output feedback, we're stuck with some linear combination. We have to feed back x1 plus 6x sub 2 in that combination, weight it, and that's why we're forced not to be able to manipulate the closed loop poles arbitrarily inside in the z-plane. But if our system is controllable, look at what K's doing. It's sneaking in there and picking up access to every one of those state vector components x. It doesn't have to work with y. That's a big assumption. And after this class, you'll have to learn how to do state space estimation if you don't have access to those state variables. And that means that you can now, if your system is not only controllable but observable, you can use the output y and the input u to reconstruct or estimate x with x hat, and use x hat in this full state feedback situation when you don't have direct measurement of the full state vector. So we're making right now, this is enough in terms of material for this semester to say, okay, Unit 8, we're assuming access to the full state feedback, or I'm sorry, to the full state vector. Unit 9, Unit 10, after class, after this semester ends, when you get into Unit 9, Unit 10, etc., then you'll worry about the estimator or observer. You might hear of common filters. Some students, maybe they're not here today. I hope you're listening. You told me you were going to listen to this. So this is a shout out to you. If you're doing common filtering for your project, then that's what you're doing. You're basically trying to maybe estimate why. A common filter a lot of times is used if you have noisy measurements. And it does a pretty good job of cleaning up or getting rid of the noise in your signals or in your output, and now you can use this cleaned up signal to control your system. Another strategy for estimating x, which we might call x hat, and using that to control the system if we can't go in and physically measure x directly. So yes, there are concerns, and the big one that I want to focus on now is not so much do we have access to the full state vector? Yes, we're assuming that, but now we also, the way we've built it so far is it would be nice to be able to tell our system where to go, or to have a non-zero reference input. Or this is now trying to tell the system where to go. Meaning, in our block diagram, this is now a bank of n delays. Here's our state vector, x of L. Here's our output matrix H that linearly combines that. And we could have multiple outputs, which just means that we have multiple rows in this output matrix H, and it does multiple linear combinations of the state vector. We have the open loop system dynamics given by phi. Whoops, I'm going to run out of space. So let me put the summing junction a little closer to the delay. There's our open loop dynamics, but now we have an input into the system, which, in addition to having full state feedback, and I've accounted for the minus sign in the gain block itself, what we want is we actually want to be able to inject a reference input that's right there. Here's our R of L. There's our reference input that we want to use to tell our system where to go. We're now introducing a new matrix. If it's single input, this may just be a scalar. We're introducing a new scalar to try to allow us to inject a reference signal into this system. Getting all choked up. I don't know why. This is very emotional, I guess, putting that reference system in, or reference signal in. But what we do know is if the system is controllable, K can be adjusted, or K can adjust the dynamics arbitrarily. So the first thing you might have to do is check controllability, and that revolves around phi and gamma. But even if we have a system that's completely controllable and we just use full state feedback, there's no way to tell the system where to go. There's no way to provide a command signal to the system. And that's what you might hear referred to as a regulator. It's just regulating the dynamics of the original system. This now you could say is a regulator system when we simply have full state feedback. U of L is equal to minus K x of L. And this regulator system is good. We don't want to throw it away. That's something good. The regulator system provides us with the desired dynamics, arbitrary movement or location of our closed loop poles. So the regulator system has desired dynamics or regulator system has desired dynamic response to any given set of initial conditions. And since I drew it in the block diagram, you should know the answer to the next question. Can we introduce a reference input? And the answer, yes, I heard you screaming. Yes. So that was a rhetorical question because I'd already shown you that it was possible by simply introducing an additional weighted signal, a reference signal, into this block diagram that we've already told how to behave by full state feedback and this gain matrix K. Now we want to be able to shape how it moves in response to reference input commands. So now this is the next topic in Unit 8, which is now reference input with state feedback. Or now telling a system where to go, you probably won't see that in journal articles in a title, but you might see tracking or that index term, or you might want to use that to search. If somebody says, oh, what kind of control problem are you doing? You might say, oh, I'm doing a tracking problem. It's probably not, where do you go? Or where do I go? They probably won't be using that terminology, but I thought that might be helpful for your grasping of what we're talking about. Now we're tracking a reference input, where the reference input now is a new signal we'll call little r of L. And this will be enough for us to just assume a scalar input or a single input system. So assume a scalar input or another way to say that is assume only one input. So let's now let U of L be more than just minus kx of L. Now U of L is what we said it needs to be. Where is U of L in this diagram? There's U of L coming out of that summing junction, and if that's the output of that summing junction, that needs to equal the inputs to that summing junction, which is minus kx of L plus n sub 1 r of L. That's the algebraic structure of our input now, U of L, with full state feedback and a non-zero reference signal. We're letting U of L equal minus kx of L plus, let's call it n sub 1 r of L. Here is now our reference input that we weight by n sub 1, that's a gain value, and use that in combination with this linear combination of state variables x. And if you wanted to sort of figure out what N1 looks like, suppose we had a single input. Then U of L is a scalar. How big is K? Well, that's going to depend on how big X is. So if X, let's say X had a dimension of 4, Nevada was now 4, X is 4 components tall, K needs to be compatible with U. The product of K and X better give us a 1 by 1. It better give us a scalar. K now needs to be a 1 by 4. Those are pretty ugly stars, but you can go out tonight and look at some prettier stars in the sky. So I'm not holding you back from seeing pretty stars, but my stars aren't very pretty. But now you can say, okay, I now said that I wanted a reference input to be a scalar. That's my R of L dimensionally. What's N sub 1 dimensionally? Is it 1 by 4 like K? Is it 2 by 2 like phi? No, it has to be such that when you multiply it by a 1 by 1, you get a 1 by 1. And a 1 by 1 is a scalar. In this case, N sub 1 needs to be that scalar. This equation, U of L is equal to minus Kx of L plus N sub 1 R of L, may have an interesting structural relationship. K and X dimensionally are bigger, or in size, bigger than N sub 1 R sub L. But their combinations end up giving you this 1 by 1 in a single reference input, single input system result. Let's now use that to work through some of these equations. Our system is X at time L plus 1 is equal to phi X of L plus gamma U of L. Our input is now not only a full state feedback, which is minus K X of L, but it also includes a reference input, which we have to put in through this gain matrix N sub 1, and a single input, single reference input system, N sub 1 is just a scalar. Let's now apply that input into our system description. We now have X of phi times X of L plus gamma times U of L, which is now minus K X of L plus N1 R of L. I'm just replacing U of L with this parameterized form, minus K X of L plus N sub 1 R of L. And let me pull things together. I have a phi minus gamma K X of L plus I have an N sub 1 that gets scaled by gamma, or N1 scales gamma. And that now is how the reference input is directed into the controlled system, where the controlled system now has a system matrix governed by phi sub c. And what are the dynamics of phi sub c? Well, those are influenced by k, and if our system is controllable, we know we can make the eigenvalues of phi sub c whatever we want. And our output y of L is now h x of L. I hope you're now asking, well, how do we pick n sub 1? We know how to pick k. We've talked about that last time and in the review today. We know how to find k, the full state feedback gain matrix k. How do we want to find n sub 1? Well, we said we want to tell the system where to go. And if I say go to 4, I might like it to go to 4. If I say go to 6, I might like it to go to 6. Well, if it's going exactly where we tell it to go, what does that tell us about the DC gain of our closed loop system? It has to be 1, doesn't it? Now, we've picked a K that might really mess up the DC gain behavior of our original system, but we still have an adjustable parameter n sub 1. That's our strategy. We want to pick n sub 1 to give us a DC gain of our closed loop system equal to 1. Let's now find our closed loop system transfer function between the reference input R and the output Y, so that we can then find a formula to solve for n sub 1. We want n sub 1 to be scaled so that if I inject 4 as a constant into my reference input, Y comes out as a 4. That's where we're going. Let's see how far we can get. That's where we're going. I'm telling you where we're going, and that's what n sub 1 is doing in this design strategy. Let's now find the transfer function from the reference input in the frequency domain, since we're talking transfer function, which will now be capital R of Z to capital Y of Z. And again, you know how to do this. What if I now Z-transform this output equation? This is a review for the final. What's the Z-transform of Y of L is equal to H X of L? This one is shift happens, isn't it? We just hit the shift key. This now says that capital Y of Z is simply equal to H X of Z. This is now the Z transform of the output equation. What if we Z-transform the closed loop dynamics? That's not much harder, is it? In this difference equation that we now have Zi times X of Z. I is just a placeholder. It's really Z times X of Z. That's the Z transform of little x of n or L plus 1 equals phi sub C X of Z. I'm going to go ahead and absorb all the phi, gamma, and k into this closed loop system matrix phi sub C plus gamma n1 R of Z. And you know the drill. Let's now combine the terms that contain X of Z we can solve this for capital X of Z by multiplying on the left both sides by the inverse of Zi minus phi sub C, so that now capital X of Z is Zi minus phi sub C inverse gamma n sub 1 R of Z. And we know what y of z, or how y of z is related to x of z. Y of z is simply h x of z. But we now have an expression for x in terms of r. This is now h zi minus phi sub c inverse gamma n sub 1 r of z. And I hope that you can now see that the closed loop transfer function with reference input, non-zero reference input, is right there. T sub c of z is in fact h zi minus phi sub c. The closed loop dynamics are hidden inside this phi sub c matrix, inverse gamma n1. We want this to have a DC gain of 1, then we would evaluate this at z equal to 1, set it equal to 1, and solve for n sub 1. I'll do that offline, but I hope you can now see that n1 is this adjustable parameter that we can use to scale this closed loop transfer function between the non-zero reference input signal and the output y. And we'll pick up somewhere close to there next time we're together.